Hi, good day. My name is Liana Samru and I am a part of the R&D team responsible for designing a device to remove solder and components from printed circuit boards. Some engineering attributes that I brought to this project are patience, attention to detail, STEM knowledge, which is science, technology, engineering, and mathematics, as well as communication skills.
Good day, my name is Abi Mahabir and I am a member of the Research and Development team. Some engineering attributes that I possess include critical thinking, analytical skills, and interpersonal skills. Thank you.
My name is David Mercury and I am a part of the Research and Development team. Engineering attributes that I intend to bring to this company are creativity, literacy in computer-aided designs, as well as communication skills. Thank you.
Good day, Executive Board. My name is Lawrence Brathwaite, and I have taken the role of Group Leader for this research and development project for our company. The engineering attributes I bring to the table are interpersonal and leadership skills, applied creativity, and an efficiency in computer-aided drawing. With that being said, I hope you enjoy the presentation. Thank you.
We compiled significant data on PCBs to ascertain the return on investment in this project. This report represents the summary of our research. A printed circuit serves as a foundation of modern electronic devices. A complex network of circuits are printed on a fiberglass board and allows for mass manufacturing and significant cost saving. Circuits are made with copper and protected by a thin layer of tin lead to prevent oxidation. Key contact points are gold-plated to ensure maximum conductivity. There are three major types of PCBs, which are single-sided, where components are on one side of the substrate, double-sided, which is used when a number of components become too much for a single-sided board, and multi-layered, which has a substrate made up of layers of printed circuits separated by layers of insulation. As we can see, patterns on a board are applied using an additive or subtractive process. Shown the problem statement of this project is that our circuit board manufacturing company needs a device to separate solder and components from computer PCBs to be reused or recycled. Therefore, from the problem statement, our aim was to design a device to separate solder and electrical components from computer PCBs. Now, in relation to our problem statement and aim, our objectives of the project were to review existing literature and patents, investigate client and user requirements which would help better our design, define design specifications and constraints, construct a metric system based on our design objectives, create design concepts for our device, and compare these concepts and select the most suitable design that we would choose.
From the extensive research done on the topic, it was found that PCBs can be broken down into two recyclable categories, non-metallic and metallic. We found two articles that provide an appropriate synopsis of the pattern seen. From the first article, titled Recycling and Disposal Technology of Non-Metallic Materials from Waste Printed Circuit Boards, we learn of the world focus on precious and general metal recovery from PCBs. We also learn of the environmental impact of not recycling PCBs, such as land degradation and groundwater contamination. The paper then goes on to present methods of recycling where the byproducts of physical recycling can be used as fillers and strengtheners, and the byproducts of chemical recycling can be used as fuel and chemical feedstock. The second literature piece is titled Novel Waste Printed Circuit Board Recycling Process with Molten Salt. This article entails an investigation of precious metal and solar removal through melting and separating with molten salts. It provides an insight on many details of the metal removal and collection, such as melting points and densities.
The first patent review includes a device created for disassembling PCB components in an environmentally friendly manner for recycling by the inventors listed on the presentation. The following diagram shows a schematic of the device apparatus. In summary, The solder melting process for removal is done by a combination of electrical and air heating means. The removal of electrical components from their circuit boards is facilitated by a shutter mechanism and rotary separation drum. The separation of solder and electronic components is achieved using a mesh vibrating screen, and used hot air is purified and recycled back into the system, thereby allowing this device to be environmentally friendly.
The second patent review is also very similar to our project's requirements. This consists of a molten bar that was used to heat the solder to its melting point. As the solder reaches its liquid state, a grabber was used to remove the solid components of the surface of the PCB. Then a vacuum was also used to remove liquid solder off holes and the surface of the circuit board.
There are a few client and user requirements that were noted from our survey results. These were: the machine should be able to operate by one switch, easy to maintain, inexpensive, safe to use, durable for a long time, easy to clean, able to separate solder and components, portability, as well as efficiency. This slide shows the survey results that helped us to formulate our client and user requirements as stated before. So some things that we noted were that the lifespan that they would want of 5 to 7 years, and there is an allocated budget, which would mean that they would want an inexpensive device. This is out of the other different questions that we also asked them. Also, from our survey results, we were able to obtain design specifications for our device, such as it should not cost over $10,000, meaning that it would be inexpensive, as well as it should last approximately 5 years, and also it should not be more than 10 feet long or 3 feet high.
This section deals with the design objectives and their respective metrics rated from worst, identified by a 1, to best, identified by a 3. The first design objective is that the device should be user-friendly. This refers to the device having easy and safe operation. The second design objective is that the device should be easy to maintain. This refers to the device having simple, durable, corrosion-resistant parts that can easily be replaced by anyone. A device which is not easily maintainable, identified by a 1 in the table, would not be cost-effective. The third objective is that the device should be durable, referring to the life expectancy in years of the device. Durability is important to achieve cost-effectiveness, since device replacements would be less frequent. The fourth objective is that the device should have a low environmental impact, referring to the use of renewable sources of energy, recyclable wastes, example biodegradable materials, and a low carbon footprint. Such a device, although being environmentally friendly, may be cost ineffective, since renewable energy systems can be very expensive. A high environmental impact device, however, results in several environmental implications, including pollution, example, emission of harmful gases. The fifth objective is that the device should be efficient. Efficiency in this case is rated by the amount of PCBs that the device can disassemble per hour and the amount of energy used. The last objective is the device should be inexpensive. This refers to the actual manufacturing costs to produce the device and simple standardized parts that can be replaced easily. If parts are too complex, including imported parts, then the parts would be more expensive to replace. Here we observe the pairwise comparison, which was discussed and completed by all members of the team. The purpose of this was to rank the design objectives according to their level of importance to the team. Each objective was compared with the remaining objectives individually. After performing calculations, the relative weighting was found for each objective. From the relative weightings, the design objective that is the most important is efficiency, having a relative weighting of 30%, and the least important objective is low environmental impact, having a relative weighting of 3%.
So now that we looked at some introduction into our PCBs, we can now form some conceptual designs from that. And first thing we do is we have a functional analysis. Now this functional analysis will help us with what we want to do in our device. So we have some inputs such as heat, electrical energy, chemical energy, where we would use this to get a result, which is heat losses and solder, which we would want after we have already done the process of removing the solder and the PCBs. So some of the functions that we would want to think about: turning on the system, introducing the PCB into the device, and then heating the solder and making sure that the solder melts and the plain board does not melt. Then removing the components and the solder and separating them and collecting them. After we have noted some of the functions that we want in our device, we can put it in a functional decomposition chart. Now this chart is basically all the functions that we would want from our device. So first we start off with a removal process, and part of the removal process we would have to obviously turn on the system and introduce PCB into the system. Then we would have to remove the solder, view the removal process, and then remove both the components and the solder, and also check the separation of the components. So all these things will be taken into consideration when we are doing this chart, as seen in the slides.
The morphological chart is a breakdown of the functions for our designs, and these functions are listed in the first column vertically. Horizontal to these functions are the different ways that these functions can be carried out. For example, transferring the PCB, this can be done using a conveyor belt, manually using a mechanical arm, and also by using rollers. For collecting the solder, this can be done using gravity, a vacuum, scraping, and also by density. For collecting the solid components of the PCB, this can be done using gravity, manually, a mechanical arm, and also by brushing off the components. The design concept table is a tabulation of all of our conceptual designs from A to D. Under these concepts are the specific ways that the functions can be carried out. For example, this table can be read using the following method. For concept A, the transportation of the PCB is done using a conveyor belt, heating of the solder using an oven, for collection of the solder, scraping, and also for removal of the electrical components of the circuit board using a horizontal vibrator. All the other concepts can be read using the same format. This slide consists of a SolidWorks drawing of conceptual design A. First, we have a conveyor belt that is used to transfer the PCB to an oven where the solder is heated to its melting point. Upon melting, it is scraped off the bottom of the oven. The PCB is then removed from the oven and clamped onto a vibrating table where the loose components from the surface of the PCB is shaken off and collected in the vibrating table. Next, we have an illustration of conceptual design B. In the first layer, the PCB is placed on to the hot plate where the solder is heated to its melting point. Upon melting, the solder is expected to run off the hot plate and be collected in the collection bucket. After this process is completed, the circuit board is moved to the layer above, where a mechanical claw is used to remove the solid components of the surface of the circuit board.
For the design concept C, the PCB is manually clamped in place and the air gun is automatically moved over the back of the PCB where it melts off the solder, and the backing knife pushes the liquefied solder into the collection area. The PCB is then gripped by a vibrating clamp and the electrical components are shaken off. We will go into more detail about this design in a minute. Design concept D entails the mounting of the board onto a molten salt bath where the solar is melted off. Simultaneously, the scraper scrapes the components off the board and into the collection area. The solar can then be retrieved from the level it settles at using the tap. Moving on to the actual design selection, this table compares each design to each other in reference to the relative weighting of the design objectives. This gives us a clear understanding of which design satisfies all objectives efficiently. In this case, design C obtained the highest total score and was therefore selected. The final design can be broken down into its individual functioning parts. Firstly, the mounting and collection frame features guides in which the removal device will be mounted. The frame utilizes two collection chambers, one for collecting solar and one for collecting components. The component collection features a hatch in which the components can be retrieved. Secondly comes the clamps which will be mounted onto the frame. These clamps can be manually closed and opened to fit varying PCB sizes. Thirdly comes the removal device which features hot air vents with a scraping knife at the back and a vibrating clamp. The removal device moves over the PCB, removing the solar and any hooked components. The device then proceeds to shake the board to remove the components. And this concludes the final design. Here are a list of relevant references. It has been a pleasure presenting this introductory video to you. On behalf of the Research and Development team, thank you for your time.